If I ask you to describe a function as a sum of frequencies, you probably immediately recall Fourier transform, which gives exact representation with infinite number of terms. Now suppose that infinity is something I can't afford, and I ask to use just a few sines or cosines. In this case, you most likely will use Fourier series, which is essentially the basic tool for that. But does it always give the most accurate approximation? Well, probably it depends on the function we're describing. But let us look at a simple example that may cause this kind of concern. Let's take a square function and approximate it on the interval from -pi to pi. The first few terms of Fourier series give the following solution, which is not bad. Well, it's not perfect, but what you actually might expect from two cosines, right? However, there are much better options. For instance, this one, which is also not perfect, but at least visually very close. This evident difference between two approximations sparks an idea that there should be other, more efficient ways describing a function as a sum of frequencies. In this video, we'll try to craft a conceptual understanding of frequency-related approximations. I'll share my feeling on the subject, which basically originates from signal processing background. We'll move forward deriving a piece of calculus that didn't get as much publicity as Fourier series, but I think definitely worth be covered. It's simple, powerful, and absolutely beautiful. I hope this video will give you an image of how flexible time-to-frequency transitions might be, and motivate to explore the subject further. The goals are probably too big for a short video. Let's not waste any time. We start with a specific question. Why is Fourier series unable to give the most accurate approximation of the square function? The answer is very simple. It doesn't model a square function. What it really models is a cycled segment of it, which apparently is quite different. The next question is, what's the point of cycling the segment? We need to have a closer look. A function of time can be transformed into a function of frequency, and we can transform it back, but we need all its frequency values on the whole infinite range. And when we are approximating a function, our goal is to set just a few frequency points that provide approximation as accurate as possible. Looks hopeless, doesn't it? And we say, okay, forget about the whole function. Let's take a fixed interval instead. Intuitively, it seems reasonable, but what does it actually mean? Function of frequency defines a function of time on infinity. Sines and cosines are infinitely long. So picking a fixed interval does not mean that there is nothing outside it, but rather we are now free to define its extension according to our needs. And that's the way we should think to make progress. A good approximation means a good extension. Fourier series offers a periodic extension that yields a very sparse function of frequency, which is zero everywhere except known points defined by the period, and we take first few of them as a low-frequency approximation. But returning to the square function, there is a clear feeling that the periodic extension doesn't work well. It's evident that to fit this cycled shape with jagged edges, we will need many harmonics. In contrast, this alternative solution behaves as if it has captured the target function itself and naturally extends it by a much larger interval. What kind of reasoning can produce a general way to such approximations? Well, here is the concept. As we figure it out, all we need is a good extension. And the more freedom for that we have, the better extension we can provide. When we use Fourier series, we reduce approximation interval from infinity to a fixed duration, and have, so to speak, one step of freedom: infinite extension versus fixed length approximation. We can take one more step and have infinite extension versus infinitesimal length approximation. As you probably guessed, we are going to use derivatives, but first I would like to give the essence of the concept using a simple but illustrative example. Suppose we are approximating a complex exponential function, an ideal one-component case. We are looking for a one-component solution with known period, which is 2π. Applying Fourier series, we use perfect interval of the function from -π to π that yields a perfect approximation. Now let's assume that instead of the interval we have a single point at t equals 0. Considering that there is only one component and that we can evaluate frequency from the period, the solution we are looking for is a complex exponential with unknown amplitude a and starting phase theta. Using the given point, we can extract amplitude and starting phase. We came to the same solution. So the both approaches find an approximation in the same form, using the same assumptions about the number of components and the period of the function. The assumptions about duration are different. In one case it's an interval, in the other a point. But despite that, solution is the same. So, is there any difference and where is any benefit? In order to answer these questions, we'll change the example a bit. Now suppose we've made a wrong assumption about the period. Interval of the function for Fourier series is incomplete, and things become more interesting. The series now has infinite number of terms, and if we take the first two of them, we get a solution that is shifted both in frequency and amplitude. However, our point approximation remains almost the same. It does have the wrong frequency which originates from the wrong assumption about the period, but despite that still has only one component and correct amplitude. Well, for one component it was easy. What if there are many components? In a more general way, the point approximation might be derived as follows. Let's examine derivatives of the solution we are looking for. We notice that they are quite simple. Each subsequent derivative is multiplied by the factor j omega. To make this easier and more readable, we'll evaluate them at 0 point and denote complex amplitude as h. In this form, it's easy to add more components and set up a system of linear equations. In the system we have an unknown vector of complex amplitudes and a matrix of frequencies that we can fill according to our assumptions about the function. To make it periodic, we may consider the target period as a constraint. To have a concrete example, let's get a point approximation of the square function we had at the beginning. First of all, we need to decide on the number of components. That's simple, we'll have two. We want them to be real, so we need symmetric pairs. The order of the system is clear. What frequencies to choose? Suppose we are looking for a periodic solution. So the first frequency equals 1. And the second harmonic is 2. We are ready to fill frequency matrix and the matrix of derivatives. We get derivatives at 0 point, which are 0, 0, 2 and 0. Solving the system with respect to h, we get symmetric complex amplitudes. Let's plot the graph of the approximation we have. Well, it fits the function at 0 point, but not as good as we might expect. However, it gets better for lower frequency. This fact we'll remember in order to analyze later. But now just notice that our approach seems to be very good at approximating polynomials. Let's try other functions. It seems to work. Let's outline what we have at the moment. We have, so to speak, Fourier series on a budget. It has seemingly the same model of the function, which is a sum of complex exponentials with the same frequencies and unknown complex amplitudes. But there is a significant difference in underlying assumptions that leads to very different results. We saw that, for at least for given examples, point-wise approximation is more efficient as far as number of components is concerned. What exactly makes it more efficient? From time domain perspective, we saw that it has more room for extension. But how does it work in frequency domain? Fourier series basically introduce infinite number of harmonics, and we bring just some of them into final approximation. But that's different for a point where we already have desired number of harmonics, and there is no so-called spectrum leakage. Looks great, doesn't it? But we still haven't exhausted all the potential yet. We are going to give that point-wise approach even more freedom. So far we made only periodic approximations, inheriting these from Fourier series, and that forced us to find only periodic extensions. But actually, we are free to choose any other we like, even non-periodic. To do that, we can remove all constraints from the frequency points and make them better fit the function. We'll go even further and make our model fit damped exponentials. In order to do that, we'll add alpha variable at the exponential and look for a solution at so-called S-plane, which is the domain of Laplace transform. It's clear that we should find S in a way that improves accuracy somehow. As you remember, we had improved accuracy for lower frequencies. It's time to reflect on this. Here is the system that we had for square function. Let's look at the derivatives that follow further. They are 0. From the other side, the frequency matrix has elements of the form j omega to the n, where n is the raw number. Considering that h doesn't depend on n, it becomes clear that when we are pushing omega towards 0, we are fitting all derivatives of the function. And this explains why we have such good results for polynomials. Generalizing this example to other functions, we can conclude that we should choose frequencies in a way to better fit subsequent derivatives. So we naturally end up with a system that has 2n unknowns and 2n length vector on the right side. How are we going to solve this? Fortunately, there is a brilliant solution to the system, which is known as Prony's method. The fact is that we can solve frequency part of the equation separately from the amplitude. At first glance, it seems impossible, but here is the trick. The system implicitly assumes that the right side is deterministic, meaning that we can predict all its values from the first n elements, regardless of variables h. Let us solve a one-component problem to develop some intuition about the method. It's clear that if we know s, we can predict the second derivative from the first. And if the function is a complex exponential, we can do it for subsequent derivatives as well, no matter what h equals to. In a two-component case, we can do it in the same way, but with a more complex predictor, which is a some combination of S1 and S2. If we look at this predictor closer, we can notice that this is a convolution of two predictors of the first order. And this means that we can extract S1 and S2 from the second order predictor as roots of the corresponding polynomial. And this is the core of the method. So, in order to find solution to the system with respect to S, first we find predictor from the given sequence of derivatives. This is done by solving a system of linear equations, and then we find roots of the polynomial. We've derived a powerful exponential model, in which all parameters are extracted from derivatives at 0 point. And I'm going to show you a couple approximation examples at the end. But before that, I'd like to add the final touch to the model. Let's include t0 into the expression and make it fit any point we want. In conclusion, I'd like to say what really amazes me about these pointwise approximations. In applied computer science, we live in a discrete reality, where everything is sampled, and we are always on a budget, since we cannot have infinite number of samples. And we are used to look at the outside world through the sampling theorem, which firmly binds us to band-limited approximations. But surprisingly, derivative opens from an unusual perspective and offers sampling of a continuous process without limiting its frequency. The other side of this is that we get a very moment-related solution, and it's difficult to know in advance how good an approximation we will get. We've considered just a few fitting techniques, and you might wonder if there are any other. My guess is there are many more of them than we actually know. The options are countless, because, as you remember, it's all about how you feel infinity around an infinitely small point.